we're going to discuss how we use some of the standard relationships to solve for the fields of linear and nonlinear dielectrics. So let's just start by reminding ourselves of the basic equations. So we define d, the electric displacement, as epsilon naught E plus P, and this is always true. And remember that we can then also go on and say that the divergence of d is equal to rho E, where rho E is the external charge. That charge has been added to the dielectric, nothing to do with the polarization. And recall that in a linear material, or linear isotropic homogeneous material, we define the polarization P is equal to epsilon naught chi E times E, the electric field. Though note that this is the total electric field, not just an applied field, and we'll see how that comes up in a minute. There are a similar set of equations for magnetic materials, but I'm just going to concentrate on electric and dielectric materials in this discussion. So I'm going to take a few examples, both from a textbook and from problems that I've set, and just go through them and discuss how we can use these relationships and standard laws of electromagnetism to derive the fields. So the first example is going to be a line of charge with a charge density of lambda per unit length, and it's going to be surrounded by a cylinder of dielectric material of radius A, and for now we're not saying what that dielectric material is. We're not saying whether it's linear or non-linear, and this system is infinite. In order to solve this problem, since we have a material and we have what is effectively external charge, that's the lambda, we're going to use the equation we just wrote up here. This equation, div d is equal to rho E. We can't use div E is equal to rho over epsilon naught, because we don't actually know what the charge density is in the material. We only know about the charge density, the free charge density, sorry, the external charge density. So we will transform that equation into an integral equation, and so we have the closed surface integral of d dot n dA is equal to the volume integral of the charge density dV. Now, in this case, we don't have a charge density, we've got a line of charge, and that means that if we consider a Gaussian surface of length L, that's going to be L times lambda. So actually let me write that we're taking a Gaussian surface. So there's a Gaussian surface. It's going to have a length of L, and it's going to have a radius R. And notice that R can be smaller or larger than A in this solution. So now we have to think about the surface integral here on the left-hand side, and the first thing we have to do is consider the direction of D. So because of the cylindrical symmetry of the system, we can say that D itself must only depend on R. It can't depend on Z or on phi, because if it did that, then there would be break of the symmetry. You can imagine, so if it depended on Z, so that would be going along. Let me just draw a Z axis here. If we depended on Z, then by shifting up and down the cylinder, we could change the value, and that wouldn't fit with the symmetry. If it depended on phi, then again, just by rotating, we could change the value, and that wouldn't fit with the symmetry. So D can only depend on R, and for an infinite system, D must lie along the R direction, R hat. Now, for a finite system, of course, that would be true near the middle. And at the edges it would have to kind of curl around, but for an infinite system we always have, for any given point on the line, there is an equal and opposite point at the other side, and so the only non-zero direction, the only direction that D can lie in, is the radial direction. So since the normal to the surface, the Gaussian surface, which is going to be a cylinder, is along the radial direction, because remember it's infinite, so we're not considering the ends, we can now say that we have the closed surface integral of D. The dot product goes to 1, and so we now have a dA. And D, we said, can only depend on R, so we can take that outside. So we'll now say, let's put a little subscript on there, dr times the surface integral over our cylinder, which of course is now just dr multiplied by 2 pi r L, and that must equal lambda L, and therefore dr is lambda over 2 pi r, and so d itself is just lambda over 2 pi r in the radial direction. So this is a fairly simple example, but the principles are the same in any problem you consider. You think about the shape and placement of the Gaussian surface, you think about symmetry or geometry arguments to work out what directions fields must take. And this is true for all R. Let's just note this. What about the electric field? So, to find E, we note that for R greater than A, we are in vacuum. We note that. R greater than A is vacuum, and we know that in vacuum D is equal to epsilon naught E, because there's nothing to polarize. So we can write E is equal to lambda over 2 pi epsilon naught R, R hat, R greater than A. Which of course is the result we would have got even without the dielectric. So it's only when we are inside the dielectric that we get that, the effect of the dielectric. Now, what about R less than A? Well, in the problem as stated, we cannot say anything about the E field for R less than A because we have not said anything about the property of the dielectric, so we can't find the polarization. So I'm just going to make a note of that. So without information on the dielectric, and that would either be a statement of how the polarization depended on position or of that it was linear, we can say nothing about E for R less than A. Let's just assume for now, so now assume it is a linear dielectric. And that we have with a relative permittivity epsilon r. In that case, now we can say that for R less than A, since it's linear, D is equal to epsilon naught epsilon r times E, and therefore we can say that E, the electric field, is lambda over 2 pi epsilon naught epsilon r times r in the r hat direction for R less than A. Now it's important to note that actually we couldn't have found this solution without first finding D. Also, even though it's linear, we couldn't solve directly for E because we would find a value of E, let's just say, without the polarization, and then we would calculate a polarization from that E. That polarization would, of course, give us polarization charges, which would then change E, which would in turn change P, and you would have to go through essentially an infinite loop. That's why we use D in this situation. Let's just do a quick consistency check. What about boundary conditions? Because you'll notice that there is a discontinuity in the electric field. We go from lambda over 2 pi epsilon naught r for R greater than A to lambda over 2 pi epsilon naught epsilon r for R less than A. So there'll be a discontinuity in E at the surface. But that's not a problem because remember that it's the E parallel to it's the E components, let me rewrite that. E parallel to the interface is conserved. And E parallel to the interface actually is equal to 0 because E parallel to the interface would either be in the phi direction or the z direction. So that'll be 0 either side of the interface, and that is conserved. What about D? Well, its components perpendicular to the interface, and those are conserved because D is the same throughout space, perpendicular, and so that is conserved. So even though there is a discontinuity in the electric field, there's no breaking of the boundary conditions. Let's think about a second example, again from a textbook. We're going to take a sphere of metal, or or of a conductor, let's say. Let's call it, it can be a metal. And it's going to, with radius A, and it's going to carry a total charge Q. Because it's a metal, because it's a conductor, that charge will of course be spread out over the surface. And so we would have a surface charge density, sigma is equal to Q over 4 pi A squared. Though that won't actually matter. The thing that matters is the total charge. And then this is going to be surrounded by a shell of linear dielectric. Out to R is equal to B. The linear dielectric is going to have the standard epsilon R. And the question is, what is the electric field? So we need to think about this for different areas. So for R less than A, i.e. inside the metal, we know from simple arguments that the electric field and the D field and the P field are all going to equal 0. Now for R greater than A, we're going to use D again. We'll find D via Gauss's theorem. Once again, we will write that the closed surface integral of D dotted with n dA is equal to the enclosed charge Q. That's just the volume integral of the charge. Again, D must be radial. That's the only direction which would obey the spherical symmetry of this system. And once again, it can't depend on the angles. And so we can pull the D outside the surface integral, and we can see that dr multiplied with the surface area of the sphere, which is 4 pi A squared, because this is where we are, sorry, no, not A squared, R squared, must equal Q, and therefore D can be written as Q over 4 pi R squared R hat for R greater than A. We've just said that D is 0 for R less than A. Is there a problem with the boundary conditions? No, because we've said that the perpendicular, the normal components of D to an interface are continuous when that interface has no external charge. But in this situation, we clearly have an external charge, it's the charge on the metal, so that's not a problem. How do we find the electric field? Well, inside the dielectric, we say that E is equal to D over epsilon R, epsilon naught epsilon R, sorry, because it's a linear dielectric. So that's equal to Q over 4 pi epsilon naught epsilon R squared in the R hat direction. Once again, we couldn't have found this without using D. We could also deduce that P is equal to chi E Q over 4 pi epsilon R squared in the R hat direction. If we wanted to, we could work out the polarization charges. So the volume polarization charge, rho P, is minus the divergence of the polarization, which in this case is going to be 1 over R d by dr of R squared P in the R direction. There are no other components. Now R squared times PR, so PR is here. R squared times PR is just a constant. It's chi Q over 4 pi epsilon R. So the differential with respect to R is 0. And so that's equal to naught. And sigma P, which is P dotted with N, will be minus chi E Q over 4 pi epsilon R A squared at R equals A, and the minus sign there is because the normal to the surface at the place where R equals A is pointing inwards, and it's plus chi E Q over 4 pi epsilon R B squared at R equals B. So these are two situations where we've had to use D because we're dealing with dielectrics which are polarized, and so we can't use E. There are times when we may have to use E, but that will typically be when we've been given a polarization. So actually, let's just do one more example to see an example of where we use bits of D and bits of E. So the consideration here, this is from a question that I set, we have a spherical shell of dielectric with a frozen permanent polarization. P is equal to K over R in the R direction. This immediately tells us that this is a nonlinear material. If you have a permanent polarization, your material must be nonlinear. So it's a spherical shell from R equals A to R equals B. Now let's consider, again, the D field, because we know that in this situation there's no external charge at all. So we can say that the divergence of D must equal 0 everywhere. Now we sometimes have to be a little bit careful, because just because the divergence of D is 0 doesn't mean that D itself is 0. But we can show that D is 0 quite easily. So first of all, let's consider R less than A, and that's where we've got vacuum, because we're inside the spherical shell. For R less than A, D must equal epsilon naught E, as always. And we can argue that E must equal 0 because there's no enclosed charge. We know that both the div E is 0 and curl E is 0, therefore that can only be 0, and that implies that D is equal to 0 for R less than A. But now, because div D is equal to 0 everywhere and D is 0 inside the centre of the shell, this implies that D is equal to naught everywhere. If you want an example of a situation where div D is 0 but D is not equal to 0, you can consider a small piece of permanently polarised material. Just if you have a straight polarisation along the material, I've done this in examples. There you've effectively got a miniature dipole where the D field is non-zero but its divergence is 0. But that's a small digression. If D is equal to 0 everywhere, then what are we going to say about the electric field? Well, the electric field, we've already said E is equal to 0 for R less than A. E must also equal 0 for R greater than greater than B, because then we're outside the shell. Again, D and E are related. Now, but between A and B, that's not true. We know that epsilon naught E plus P must equal 0, and therefore, because that's D, E must equal minus P divided by epsilon naught, which in this case is minus K over epsilon naught R in the R direction. So in this case, with a permanent polarization and no external charge, the electric field and the polarization cancel each other out. You can get the same result for E, which is reassuring, simply by thinking about the charges. So by considering the polarization charges, rho P and sigma P. That's something that I've gone through in the worked answers to a problem sheet, so I won't go through them now. But just to note that rho P is minus K over R squared for A less than R less than B, and sigma P you get only on the surfaces. It's K over B at R equals B and minus K over A at R equals A. And then when you just think about the electric field, again, you're going to use a spherical Gaussian surface, and you need to consider all of the enclosed charge. So what we've done is we've just shown some examples of how to use D and E and P to calculate the properties of materials, both for linear and nonlinear dielectrics.